Hey guys, so Unit 2, Lesson 5, Combining and Inverse Functions. This is going to be hopefully a shorter video than the one already posted. So we're going to go fairly quickly through this. We're going to look at two things, how to do different operations with two different functions, and then how to find the inverse of those functions as well. And so by operations, I'm talking about just adding, subtracting, multiplying, and dividing them. There's two ways you can express that. You can say f plus g of x. So this would be said f plus g of x, or f of x plus g of x. And so it doesn't matter how you say that, but these are the two notations that you would see for those. The domains of your resulting functions are always the domain of f and the domain of g put together. And so you have to make sure that you consider them individually and then where that overlap is going to be in those domains. All right, so let's look at this. So for f of x, it's x minus 4, and g of x is x squared plus 1. So if I'm doing g plus f, then I am taking my g function and I am then adding my f function. And so I'm doing x squared plus 1 plus x minus 4. With addition, I don't really need that plus or the parentheses there, so I'm just going to combine my like terms and get x squared plus x minus 3. And so this is g plus f of x. Right, I'm going to go ahead and do the rest of these fairly quickly. So g minus f, make sure you watch your signs there. So again, I have that x squared plus 1, but this time I'm subtracting the x minus 4. And so with that in mind, everything in there will switch signs. So I have x squared minus x. This becomes plus. So I have plus 5. G of f of x. We're looking at taking that x squared plus 1 and then multiplying it by the x minus 4. I forgot to color code that for you. With a binomial times a binomial, that means then FOIL. So we have x cubed minus 4x squared plus x minus 4. No like terms to combine, so that is my g of f function. And then last we have g over f of x. So we have our x squared plus 1 over top our x minus 4. If the top factors, then this would simplify. This one does not, and so that is your answer. Then, looking at our resulting looking at our resulting functions with when we have f and g, we can determine what that domain is. So the domain for this, it's a quadratic, so you have negative infinity to positive infinity. Here's another quadratic. Remember, you can also state that as all real numbers. These are the same thing. It doesn't matter. So we're, again, looking at this resulting function, and we have both f and g combined. Okay. Here we have a cubic function. So if you think about the domain for that, it would be all real numbers as well, or negative infinity to positive infinity. Those are the graphs that go like this. And then this last one, we have to think about the bottom here. Your domain has a restriction where x cannot be 4 because it's a rational expression. And so we are going from negative infinity to 4. And then we are going from 4 to infinity with that gap in between. Right, so, but looking again, once more at that resulting function and what its domain would be. So don't worry about the domains of them individually. That resulting function, after you simplify it, will show you what that can be. All right. And so I'm not going to do this one all the way out. If you need a second example, then turn to the long one, but I want you to go ahead and try this. So you can pause the video now, try this yourself. When you hit play, the answer will be displayed on the screen. So go ahead and hit pause now. Okay, so here you go. Add, subtract, multiply, and divide. The division one, I tried to factor this out. It did not factor in a way where I could get x minus 1 as one of them. So I know that doesn't reduce. But domain restriction is 1, makes the bottom 0. And so we need to use that in our domain. All right, when we compose functions, we're putting one of them inside of the other. Always begin your work from the inside out, and then just keep working your way out from the inside. You'll see this written two ways. It looks kind of like fog. The order here does matter. This means we're putting g into f. All right, the function of f of g of x. So x goes in g goes in f. All right, so fog is different than GOF, but it doesn't matter how you notate this. Again, we're going to work from the inside out as far as how we substitute. All right. So we have f is the square root of x, g is x squared plus 1, and we want to find g of f of x. So we're leaving x the same. There's no number here. And we replace that in the g. We square and add 1. Well, we're replacing x with x, so nothing changes. So this is still g. We're going to take this whole thing and plug it into f. So we're going to replace this x with this whole thing. All right, so that gives us square root of x squared plus 1. Remember this being what you had before as x. Okay. All right, so let's look at a couple of these. So we're doing g of f of 2. So the negative 2 goes into the f first. So we have f of negative 2 is equal to 3 times negative 2 minus 5, which is negative 6 minus 5 is negative 11. Then we're going to take this negative 11 and plug it into g. So whatever you get here goes into g. So I'm doing g of negative 11, which is 2 minus negative 11 squared, which is 2 minus 121. So it's negative 119. And that's your final answer on that one. So again, go ahead and pause this video and try this one yourself. Notice we're plugging this into g, but then taking that answer and plugging it into g again. Okay, go ahead and check your answer. You can also do, knowing the fact that we're plugging this in twice, you could have written this as like 2 minus 3 squared, where this is your 2. Actually, we need to square this twice if you do that. So it gets a little muddled, but you're welcome to try to do it that way. There's a lot of parentheses. Anyway, so I wouldn't mess with that with just regular numbers. Sometimes when you have variables, you have to do that, like what we're getting ready to practice here. And so using the algebra to state these examples. So let's do f of g first. F is this, g is this. So we're essentially evaluating f for the g function x plus 3. All right, so we did this in lesson 1. All right, but that x plus 3, you just need to know that that comes from the fact that we're plugging in g to f. So where there's an x squared, I put x plus 3 squared, and then minus 5. So that's x squared plus 6x plus 9 minus 5. So f of g is x squared plus 6x plus 4. Domain for this resulting function is all real numbers because it is a quadratic. And this is f of g. So let's look then at g of f. And try to, mine kind of ran together there, you can't tell it's open. There's a difference between multiplying and composing, right? And the order of those matters. And so here we're taking g of f of x, which means we're taking our f of x function and plugging it right here. So really we're taking g of x squared minus 5. And so in your g function where there is an x, we replace it with x squared minus 5. The plus 3 stays the same. These parentheses with addition don't matter. So g of f is equal to x squared minus 2, where your domain is still all real numbers. And that's as far as you can go, right? So I want you to try these last two. So once more, pause the video and give it a shot. Okay, so go ahead and check your answers there. Domain on both of these is all real numbers because we're either getting quadratics or linear. And then here is your f of f and your g of g. All right, so once again, it doesn't matter how it's written in terms of if it specifies f of g of x or not. If it just has f of g, you're going to apply that. But you do need to pay attention to function names and the order in which you're plugging in. So we're in this first one taking f of g, so we're taking the x squared and plugging it into our f function. So that means that we have 1 over x squared. The domain for this, we have a domain restriction at 0 because it's a rational expression. So we go negative infinity to 0, and then 0 to infinity. Whereas in g of h, we're taking our h function and plugging it in here, sorry. Okay, so we're going to do x squared, but our x becomes square root of x, and so we have x square root of x squared. And so that is just x. So your domain is then all real numbers. And that is your g of h. All right, so this is a good place to stop if you need a break from these notes, because we're going to talk about inverse functions. And so that's a little bit different in terms of what we're looking for, but how we find it is real similar. And actually, I'm going to have to go back here and correct myself real quick. I made a mistake on domain. Sorry, the domain for this function we need to look at, because we plugged h into g, we need to consider that with our domain. My x values still need to be positive, and so we're going to start at 0 and go towards infinity. And so base it off of the one you plug into the other, as well as that resulting function when you're looking at those. So as long as your second function doesn't have any restrictions to begin with, you don't have to worry too much about that. Okay. Yeah. Okay, so noting the difference between an inverse and a composition, you'll see a difference in your notations. So a composition is that f of g with that open circle of x. With an inverse, we're going to see f of -1 of x. What could be potentially confusing about this is this does not mean that we're flipping it, where with negative exponents, when you look at those, if you have like x to the -1, that means 1 over x. We're not, that's not what we're doing here. And so just ignore that. Okay. We're finding a function that undoes what we have done. And so where if we have a line, we now have the inverse of that line. And that's a better idea of what we're doing in this particular case than what you did before. And so just a little example, feet and yards and feet. Sorry, the formatting on that's a little bit off. We have 3 feet for 1 yard, 6 for 2. So when we're looking at our x and our y's, we'll see that if we take x and divide it by 3, then that's this function. Divide by 3 is 1, divide by 3 is 2, divide by 3, and so on. Here, though, we're going the other way. So we're taking our x values and we're multiplying them by 3 to get that function. And so those are inverses. Here we're dividing by 3, here we're multiplying by 3. And so when we're going from a function to its inverse, we'll see that the inputs and the outputs flip-flop. And so whereas before these are inputs, these are outputs, they have now traded places over here. The domain and range will also flip places. So this one's a little hard to tell because your domain and your range are both all real numbers. But we can look at a set of actual numbers and tell that too. So like our domain values here are 1, -3, 2, -1. That becomes your range in its inverse, right? So where f of 1 is equal to 5 in this function, f of negative, the inverse of f at 5 will equal 1. And so f of the inverse of -1, if we look up here, when it was -1, it was -3. And so oh, sorry, we're looking at y values. I didn't see that one. And we have our -1, and so we're looking at getting the x value instead. So when you're using inverses, look at your y values. And here we're taking the inverse of the function at 1. Well, when the function is at 1, we get 5. And so we're taking the inverse function at 5, which is 1. So you can see that f and inverse of f cancel each other out, hopefully. If not, you can just plug it in and solve. But like here, for example, if I do f and f of -1 of 1, so that's an x, and these will cancel, and this is just 1. Right? Not all functions will have inverses. You have to make sure that everything is flipping and that it works out. So here, the function t pairs the month as a number with the average high temperature of this island in Florida. So here's your t function. What we need to look to see is the inverse a function. And so if we look, keep in mind these are our x values, right? We have 6, 7, 8, 9, 10. These are our y values. But if we flip this table and we make our x values, if we make these our x values and these are y values, then hopefully you'll see right here, the x values are repeating. And so because the x values are repeating, this is not a function. So there is not a function, so it's not an inverse. All right, if a function's one-to-one, it will always be invertible. A function's one-to-one if no two inputs have the same output. So a function is one-to-one if there are no repeated ranges. And so it's a function if the x's don't repeat. It's a one-to-one function if the y's also don't repeat. And so that's what you're looking for to see if it has an inverse. So you can decide graphically using horizontal line test or the HLT. And if you think about that, that means because when we invert it, it will pass the vertical line test. So it has to pass your horizontal line test. So an inverse only exists if a horizontal line crosses once. So again, opposite of our vertical line test, because we are turning this on its side essentially. Okay, so you can perform that to see if it's invertible. So for example, if I draw a horizontal line here, here, and here, this is not invertible. It doesn't mean this is not a function. It means its inverse is not a function. Here on this one, we can draw as many horizontal lines as we want. It does have a horizontal asymptote here, but there's no repeated values. So this is, yes, invertible. Okay, and then last thing here, check if it's one-to-one. We're going to find the inverses or calculate them. So use the HLT to see if you can even do it. Rewrite it from function notation to standard notation, and then flip-flop your x and y values because we saw in the tables that's what's going to happen with our numbers. Solve it, get it back into y form, and then rewrite it into function notation but use the inverse notation. Make sure that it is one-to-one, it passes the HLT, but if it doesn't, then we need to restrict the domain so that it remains a function. We want our inverse to be an actual function. All right, so what I mean by that, let's go ahead and do this algebraically step by step. So making sure it passes the HLT, you can type it in your graphing calculator or just, picture what it looks like. This is a line. It will pass the horizontal line test. So I'm going to rewrite this as y equals 3x plus 2. Then my next step is to flip the y and the x around. So everything else is staying the same. This becomes x, this becomes y. Then I solve this for y so that I could actually graph it again. So x minus 2 equals 3y. Y equals x minus 2 over 3. Okay, well, this is still linear, and so it's going to graph a line, so I don't need to restrict the domain. So I'm going to just rewrite my final answer in inverse function notation. And this is now my inverse function. Right, again, passes the HLT. Okay, so let's do another one here. Y equals square root of 2x minus 1. Flip-flop your x and y, so x equals square root of 2y minus 1, and then solve it. So squaring both sides, x squared equals 2y minus 1, x squared plus 1 equals 2y, so y equals x squared plus 1 all over 2, or put them individually over 2, it doesn't matter. But this does not pass your HLT, right? You can't draw a horizontal line, so it fails, which means we need to restrict our domain. And if we look back at our original function, we can see why we need to restrict our domain. This is not an inverse. They're not exact opposites. This only graphs the positive values. And so we want to just have essentially this side of our quadratic. And so we're going to restrict our domain here to 0 to infinity. All right, so last time I'm going to have you pause this video one more time and work your way through these, and then just resume to check your answers. Okay, and there's your last two answers. This one, because of the fact that we have two y's in non-like terms, we had to use that method from Unit 1, where we're factoring out that y, so getting all your y's on one side. So getting rid of your fraction first. We get here, move all your y's to one side, and then factor it out and divide. It does still pass your HLT, so you can rewrite it as an invertible function. This one, being a quadratic, won't pass your HLT to begin with, so it is not invertible. All right, have a good night.